In this video, we're going to finish up our discussion of transient vibrations. So here we're going to discuss convolution. So we've shown previously that the response to an impulse load applied at time t equals 0 is given as x of t is equal to f naught delta t over mp sine pt, where f naught delta t is the magnitude of the impulse. We can apply impulses at later times, for example t prime. And the response is defined as f naught delta t over mp times sine of p times t minus t prime, where t is, and this is valid for all t greater than t prime. So basically it's valid for all times after the impulse is applied, if the impulse is applied at t prime. So this is the elapsed time in the response since t equals 0. So, and you can see if t prime was equal to 0, we would recover the response when the impulse is applied at t equals 0. So this assumes that the mass is at rest at time t prime, and it gives us the position of the mass at time t, which is after the impulse has been applied. So essentially this represents the change in the response compared to what would have occurred if the impulse had not been applied. So we can consider some arbitrary function as a series of impulses, an infinite number with infinitely small duration. The response will be affected by the sum of all of the impulses that occurred before the time t. So the application of an impulse, ft prime dt prime at t prime, will have an effect on the position of the mass for all later times t greater than t prime, with the position of the mass at time t given by this expression. So dx is f at t prime dt prime divided by mp times sine p t minus t prime. So we can move this dt prime to the end of the equation here. So this represents the change in response to only this one impulse. To get the actual position, we need to integrate all of the effects of all the previous individual pulses. So the response of the system is equal to 1 over mp times the integral of this equation. So f of t prime sine pt minus t prime dt prime. So this will give us essentially the sum of all of the response of all of the impulses up to the time t prime that we're considering, or up to the time t, sorry, that we're considering. Where t prime here is simply a dummy variable in the equation. So this expression is known as Duhamel's integral, and it is a special form which gives the position x of t for an arbitrary load f of t. So this assumes that the initial conditions at time t equals 0 that the system was at rest at time t equals 0. So x of 0 is 0 and x dot of 0 is 0. If the initial conditions were more general, so it had some initial displacement x naught and some initial velocity v naught, then the equation is replaced by this form, which includes that homogeneous part of the solution as well as the particular part given by Duhamel's integral. So this is the response at time t in the absence of the impulse, and this is the change in the response due to the sum of all of the impulses, where we're representing an arbitrary function as this sum of impulses one after another. Now, we can also apply convolution in cases of base excitation. So in some situations, the force is not applied directly to the mass, but instead the support structure is given a motion y of t. The equation of motion in this case is mx double dot plus kx is equal to ky of t. So now f of t is replaced by ky of t, and Duhamel's integral becomes this expression here. So we've replaced f of t as f of t prime as ky of t prime. And we can bring the k out of the integral, and we get this expression here. And now, since we know that k over m is equal to p squared, this can be written as x of t is equal to p times the integral y of t prime sine pt minus t prime dt prime. So in this case, y of t is now the motion of the base. So given the motion of the base as some function, we can calculate the motion of the mass itself. So far we've only considered the undamped situation, but we can actually consider viscous damping in using convolution as well. So if we want to consider the response of a viscously damped spring mass system subject to an impulse load, we can start with assuming that the initial conditions are 0. So initially it's at rest, 0 position, 0 velocity, before any impulses are applied. Similar to the undamped case, the initial conditions just after the impulse is applied are given as shown here. The response of the subsequent free vibration is then this familiar expression. With the initial conditions given on the previous slide, we can find A and B. So the response then becomes F naught delta T over MP times the square root of 1 minus eta squared e to the minus eta pt sine square root of 1 minus eta squared pt. If the impulse was applied at some later time, t prime, the response would be given as shown here. So we've just replaced our t with t minus t prime. And this applies for all t greater than t prime. As before, if we consider an arbitrary forcing function to be composed of an infinite number of infinitesimal impulses, the response at time t due to the impulse applied at some earlier time t prime is given by this. And the response then becomes this integral from 0 to t. Now this equation only works for the case where our initial conditions before the impulses are applied were x of 0 is 0 and x dot of 0 is 0. So initially the system was at rest. Then we apply this function that we're considering, a series of impulses. This would be our response in a damped situation, a damped spring mass system. If we want to generalize it for different initial conditions, then we can do that in the same way that we did for the undamped convolution approach.